So let's begin with Lesson 2 in our Math 215 class. First thing I wanted to talk about is actually one of the motivations for studying differential equations. So let's see what type of problems we can solve with just using the basic integration techniques that you talked about yesterday. So here's a simple problem that you might have run into. This is, of course, a classic problem. It's called the coffee problem. And the problem is really simple. If you're a coffee drinker or you know someone who is, you'll notice that once you pour a cup of coffee, you have maybe at most 10 minutes to figure out to drink your coffee before it actually gets cold. So one reason we want to study this problem is because it's going to be a very good example of a first order differential equation, and almost just the type that you studied yesterday, except we're going to have to develop a little new method to solve it. This one's going to be non-homogeneous. So let's see how we can model this problem. So let's try to figure out first if we can call the actual temperature of the coffee something. Let's call it maybe T of T. And one thing you'll notice about coffee is that if we think through it, if we're going to model the temperature of the coffee, that's our goal, we kind of have to know something about other variables in the problem, or at least a context for this variable temperature. So, of course, the coffee is usually, when it comes off the coffee pot, pretty hot, usually about maybe, let's say, 150 degrees Fahrenheit. So that's our initial temperature. We're interested in finding our final temperature, our temperature at any time t. But of course, if the coffee is at 150 degrees, we really have to situate this problem within the grander scheme of where we are. If we're in a room that is already at 150 degrees, chances are the temperature of the coffee is not really going to change. Part of the reason why our coffee cools down so quickly is because the ambient temperature is much lower compared to the coffee's temperature. So let's say our ambient temperature, let's call that T sub 0, is somewhere around maybe 74 degrees Fahrenheit. So that's our room temperature, just about. So what's one of the things that we can extract from this? So far we have for our coffee problem, simple model. We want to find the temperature T at any time. We know that the initial temperature is 150 degrees Fahrenheit. And we also know that our ambient temperature is 74 degrees. So we can pretty much see that based on our sort of conception of why the coffee cools down, what really matters is the quantity T minus T0. So this is the temperature difference, and we sort of intuitively know that it's only when you have a temperature difference that the coffee is going to change temperature. And we kind of know, just based on our own experience, that coffee at 150 degrees Fahrenheit cools down to 74 degrees Fahrenheit. So our coffee is cooling down. Now, let's think about this in terms of derivatives. So that implies that the temperature is not only changing, but more precisely, it's decreasing. All right? So we figure this out just by thinking through what coffee does when we actually take it off the pot. Okay, so now we know that the temperature is changing and it's decreasing. So let's figure out how we model that mathematically. So remember that if a function f of x is decreasing, then we know something about its derivative. So think back to your Calc 1 knowledge. What do you think you know about its derivative? that it's less than 0. So we can use this here. So we're sort of going to invert that, and we're going to add the if and only if. So we're going to say if the derivative is less than 0, then the function is decreasing. So this is true in all but a few cases that we're not really going to need for our example. So we know for sure that in our case, since our temperature is changing and decreasing, we can model that mathematically with the derivative being negative. So here's another sort of piece of the puzzle. So at this point, we've gotten a few pieces that we want to link together. The temperature is decreasing, and that's our mathematical statement for that. And we also know that the amount of temperature decrease somehow depends on this difference between the temperature of the coffee and the temperature of the ambient surroundings. Again, if the coffee was at 74 degrees, then there's no reason, we think, why it would decrease or increase from that temperature. It's the fact that there's a difference in temperature that actually leads to the temperature change. So let's put these two things together. Temperature is decreasing, and it somehow has to do something with this. Great. So what we're basically getting at is something called Newton's law of cooling. So let's state Newton's law of cooling. It's a pretty simple statement, and it's exactly the sort of endpoint of the concept that we have just been discussing, that the somehow change in temperature of an object is related to its difference between its temperature and its surroundings. And that's pretty much the content. So let's read this off here. The rate of change, oops, I skipped here, of the temperature of an object is proportional to the difference between its own temperature and the ambient temperature. So if we apply this in our context, this is going to give us a differential equation, which is going to be first order. But as we'll see, it's non-homogeneous. So that's going to require a new solving method. So let's just translate everything. So the rate of change of the temperature. So in our case, mathematically speaking, that's exactly what T prime of T is. Of an object is proportional to, so already the wording is giving us an equation. T prime of T is some number times something. That's what it means to be proportional to. And here's the statement. The difference, so there's a subtraction sign somewhere, between its own temperature, that was our variable T of T, and the ambient temperature, that was our T sub 0. Okay? So this is exactly what Newton's law of cooling tells us. Now there's one little thing we have to add here. Remember when we talked about this coffee problem, we knew beforehand that the change in temperature was going to be negative because the coffee was going to cool down to the room temperature. So that little bit of information tells us that this number should be a negative number. So we're going to enforce that by saying that this value k is bigger than 0. So this is our model, our first order differential equation for the temperature T that we're going to use. So let's see how we can solve that. So here's the equation that we got from our analysis of Newton's law of cooling for our coffee problem. Let's rearrange things a little bit. So let's distribute out this minus kt and add to it the other distribution. And let's simplify that to the form that we're more familiar with so that we can classify it. Okay. And we can write this also in our sort of Leibniz notation. And in this form, we can see pretty clearly that it's a first order differential equation. And since it's a new variable, let's sort of fit this into what we'll be seeing more often, which is the general form of a first order differential equation. It looks something like this. So if we compare these two, we can sort of pick off what these things are. So our sort of a of t function here is just the constant k, and our b of t function is also a constant, k times the ambient temperature. So this is one of the simple cases where a and b are both constants, they're just numbers. Okay? But it is non-homogeneous because b is not equal to 0. So we don't quite know how to solve that yet. Yesterday you learned from Professor Tannenhauser how to solve the homogeneous case when b is equal to 0. And what we did there, if you remember, was we moved this to the right-hand side, then we divided by y. So that's not really going to help us here, and let's see why not. If we rewrite our equation for our coffee problem and try to move over the term that essentially represents a of t times y, and then divide through, we end up with a little bit of a problem. See, before, when this b of t was 0, we would have been left with a function of t here. And then we'd be able to say this is d by dt of the natural log of t equals this. If you go back to your notes on what we did yesterday, that's exactly what happened. So this wouldn't have been there, and we would have been able to integrate very easily. The problem now is that you have a t here, and you also have a t here. So we can't just integrate both sides of the equation because we don't know what t is. So we can't integrate it. So this tells us that this is not the way we want to go to solve a non-homogeneous first order equation. So let's put our coffee problem on hold for a second, since it is a bit on the abstract side. And let's start off with a simpler example, something that we can work on concretely and try to solve this. If we can understand that first, then we can use what we learned to make some sense about why coffee cools down so quickly. So here's a first order equation. Here's our a of t, and we also know it's non-homogeneous since b of t is not 0. So even though this is a non-homogeneous first order equation, let's see if we can capitalize on what you learned yesterday to try to solve it. So recall from yesterday that what we did to solve equations that looked homogeneous was that we divided by y, and we put all the y's on one side and all the t's on the other. What that allowed us to do is then to say, okay, the left-hand side is the derivative of ln of y. And the right-hand side doesn't have any y's anymore. So what I can do is just integrate both sides and then exponentiate and then get a solution. So that's very nice, but in this general case, as we just talked about, it's not going to work. So there's one thing that we can extract here. And this is what really made the problem solvable. Somehow getting everything on one side to be the derivative of some function of y, and everything on the right-hand side to not depend on y. So that's exactly what we want to do for this problem. So let's see how we can get that to work. So when you see the solution technique at first, what I'm about to describe, it seems a little mysterious, but we'll see why this works. So let's introduce a new function we'll call it mu of t. And this function is going to have play an important role. It's going to be called an integrating factor. And we'll see why in a second. So with this new function, the idea is going to be to multiply through by this mu of t. So we're going to multiply the entire equation by mu. So that means every single term gets a mu in there. And then now the idea is to essentially do what we did with this d by dt of ln of y business. We're going to enforce, we're going to require that the thing on the left-hand side be the derivative with respect to t of mu of t times y. So notice that this is now taking the place of the ln of y in the first order homogeneous case. And requiring this is something that we can do just as a solution technique. So there's no sort of special caveat. But if we are going to say that this is equal, then there are things that are going to have to be related. So on the right-hand side here, for example, this is the derivative of a product of functions. So we can apply the product rule. So the derivative of the first times the second plus the first derivative of the second. And if this really is going to be an equality, we have to set these two terms equal to each other. So the first term here, mu times y prime, that's the same as that term here, mu times y prime. So we can actually subtract that term from both sides to get rid of it. And what we're left with is an equation that's going to tell us how to solve for mu. So we're left with this equation. You'll notice that it has mu on both sides, so we can cancel that out. And that leaves us with mu prime of t equals mu of t divided by t. And this is an equation that we know how to solve. This is exactly a first order homogeneous equation. And to see that, we can rewrite it in its more common form like that. Okay? So this equation we know how to solve pretty easily. We know that the solution is mu of t is some number times e to the integral of this quantity here, 1 over t dt. And again, we get this just by doing the exact same solution procedure that we did for the first order homogeneous case. Divide by mu. The left side becomes d by dt of ln of mu. And we integrate the right side. And that's where this integral of 1 over t dt comes from. So the integral of 1 over t is ln of t. You exponentiate that and you get t. So we've actually been able to solve for our mu function. It's just a number times t. And what we'll always do when we find these integrating factors is set this integration constant equal to 1. So we do that because the integration constant we really care about is going to come in at the very end of the problem once we solve for y from our actual original problem. So this integration constant we don't need to worry about. Great, so now we have our mu of t equals t. We've solved for that function. And let's go back to what we had gotten after we multiplied everything. So this was the equation that we had after we multiplied everything. And now that mu of t is t, we can sort of just read off what we'll get. Ty prime plus, these t's will cancel, so just a y. So we get ty prime plus just a y. And we can read off the right-hand side. If mu is t, then this is just t cubed. Okay? So at this point, you might be wondering, why go through all that trouble? And the answer is because now, if we look at the left-hand side, this is exactly equal to the derivative of t times y. And we can check that really quickly. This is a product rule. The derivative of t is 1 times y. That gives you that term. Plus t times the derivative of y, and that gives you that term. And it sort of shouldn't be surprising because that's, oh, pardon that, that's exactly what we got over here. Right? So that's exactly our setting this equal to the derivative of mu times y. That's how we found mu in the first place. So that tells us that we've gotten here. And at this point, we've sort of achieved the same thing we achieved for the first order homogeneous case. The left-hand side is a derivative of a product, or in this case, a product. The right-hand side doesn't involve any y's. So we can integrate both sides to get 1/3 t cubed plus c. Oh, I noticed I made a small mistake here. This should have been a t cubed to begin with. So we integrate t cubed here. So we get 1/4 t to the 4th plus some constant. And then we solve here for y. So what is our y going to be? We'll just divide by t. So we get 1/4 t cubed plus c over t. Okay. And that is our solution to our original problem. Notice that this is what I was mentioning earlier. Here is our arbitrary constant c. So if we're going to need to impose any conditions, and we'll talk about that in a bit, we can use that c standing there. So now that we've solved our first non-homogeneous equation, we want to see if we can go back and try to extract some sort of general principle that we can use for other equations. So the very first place that we started with was introducing an integrating factor. We multiplied through by that, and then we enforced that whatever we got on the left-hand side be the derivative of the integrating factor times y. Now that led us to a differential equation for mu. What we want to do here is sort of notice one thing. So this was mu prime equals mu. Notice it was times 1/t. Right? There's a 1/t here in disguise. That 1/t is exactly what was in front of the y, which is usually what we call a of t. So let's write some of that down. So in general, for a general first order non-homogeneous equation, if we were to do the same exact technique and multiply through by mu, and then enforce that the left-hand side be d by dt of mu times y, then if we work this out just like we did before with the product rule, so that's this derivative, and then set that equal to this left-hand side, and we compare both sides. We again see a mu times y prime on both sides, so they cancel. And we see again a y here, so they cancel. So this is exactly what we just saw. The differential equation that we get for mu is mu prime equals a of t times mu. And we know how to solve that by using the techniques you learned yesterday. So we know that the solution there is k times e to the integral of mu dt. And again, we're going to say that this k is equal to 1 because, as we saw with the previous problem, we're going to leave all the integration constants for the end. So our takeaway from here is that we now have a way, a formula, to figure out what mu is just from looking at the differential equation. And I realized that I made a slight little mistake here. Instead of mu dt, this should have been a of t dt. Okay? So this is our formula for the integrating factor, mu. So our solution technique from now on is pretty straightforward. So let's write that down. If we want to solve y prime plus a of ty equals b of t, any non-homogeneous first order linear equation, there's a simple procedure that we can follow. So the first thing we want to do is find the integrating factor. And that's going to involve integrating a of t and then exponentiating that. After we do that, we will multiply through by mu of t. And once we do that, we're guaranteed, remember, because that's how we got into this mu business to begin with, that the left-hand side is the derivative of mu times y. And at that point, it becomes essentially that last step in our previous solution technique for the homogeneous ones. So we would pick up where that left off and integrate both sides. All right, so that's our technique for solving non-homogeneous first-order linear equations. And let's see how much of this makes perfect sense and try an in-class exercise. This is going to be problem 4 on page 10 of your textbook. In case you don't have that in front of you, let me just write this up for you. And ignore the initial condition for now. We'll talk about that in a second. And just see if you can solve the differential equation itself. If you're watching this video by yourself, just give this a try. If you're watching with someone else, give this a try for maybe a minute or two, and then turn to that person and see if you all can compare answers. And we'll come back and talk about the solution to this. All right, so let's talk about the solution to our first order linear non-homogeneous problem. So let's follow our step-by-step. First step is to, of course, recognize that it's of that form. We know that because it's definitely first order. Highest derivative is order is 1. And we know that b of t here is not 0. So we know it's non-homogeneous. Since we're going to need to identify it anyway, let's identify our a of t. So that's always what's multiplying y. So that's pretty simple. We can plug that into our formula for the multiplier. In this case, it's just integrating 1 dt. So that just gives us e to the t. That sounds good. Now that we have our multiplier, we'll multiply through the entire equation by the integrating factor. And on the right-hand side, we're going to simplify a bit. So e to the t times e to the t is e to the 2t. So based on everything we just talked about, we know that this left-hand side now, and we can check that pretty easily if you ever are in doubt, is the derivative of the product of the multiplier and y. And the right-hand side is just t e to the 2t. So we can integrate both sides. And this is where, as you saw yesterday, a lot of your integration techniques come in handy. All right? So this doesn't seem like we're going to be able to do it with a u substitution. But if u substitution doesn't work, the next logical thing to try is an integration by parts. So let's try an integration by parts. Let's let u be t, du dt, and dv be e to the 2t. So that means we have to integrate this to get v. And exponentials are pretty easy to integrate. All right. So our integration by parts formula tells us we get u times v minus the integral of v du. So that works out rather nicely here. We have our original product term minus, and we know how to integrate this. We just get another 1/2 e to the 2t. And don't forget the plus c. That's always important to give us our parameter. All right, so we have our left-hand side, we have our right-hand side, so we can solve for y of t pretty easily here. We're going to divide through by e to the t. So everything here that had an e to the t, we're dividing by, e to the 2t, we're dividing by e to the t. And that leaves us with this. Remember, e to the minus t is 1 over e to the t. So this is just a quicker way of writing that. And that's our solution for this problem using our multiplier approach. Now that we've solved the problem, let's move on, and let me make one quick remark, which is very important. So this sort of might have gotten lost, but I want to emphasize the point because it can get a little tricky. So in order to use this solution technique, by which I mean this idea of finding the integrating factor and multiplying through, we made a crucial assumption. And our assumption was that the first order linear differential equation had the form y prime plus a of ty equals b of t, our sort of general form. But what I really want to point out here, that's the crucial assumption, is that y prime had only the number 1 multiplying it. This is very important because let's say we come across a differential equation that looks like, I don't know, t cubed y prime plus y equals e to the t. So you might be tempted to say, okay, I'm going to find my integrating factor mu, and I'm going to identify here that a of t is 1 and b of t is e to the t. So I'm just going to do e to the integral of 1 dt. So my integrating factor is e to the t. Unfortunately, that's not going to get you the correct answer. And the reason is because the whole way that we found this formula was by literally assuming that this was the starting point. If you change the starting point, then you'll change the formula for mu, and it will no longer be given by this. So make sure that if you're actually going to solve a problem where y prime does not have a coefficient that's 1, you make it have a coefficient that's 1 by just dividing through by whatever's in front of it. That's very important. So now it's in this sort of standard form, and now we can use our mu formula. And notice that, as advertised, the a of t is different. It's 1 over t cubed that we're integrating instead of 1. So this will give us a different mu of t here than we would have gotten there. So just keep that in mind when you're solving these first order non-homogeneous equations. So let's talk now about the second part of that problem. If we go back there, you'll notice that there's a bit that I said we would skip initially, and that's the initial condition. So let's go back and see if we can apply this initial condition. Let's take the solution that we had derived, and maybe it will let me copy all of it. Looks like it will. Great, so there's our solution. And what we want to do now is we want to apply the initial condition, y of 0 equals 2. Now this is the first way that you can apply initial conditions. So we'll say method 1 to apply the initial condition. So method 1 is you solve the entire problem, leaving in your arbitrary constant, and then you use the initial condition. So 2 is equal to y of 0. That literally means I'm going to plug in 0 everywhere I see a t. So here I'm going to have 0 times stuff, so that goes away. E to the 0 I know is 1, so that gives me a minus 1/4. Plus c, I have another e to the 0, which is also 1. So from here we get a simple equation for c. c equals 2 plus 1/4. So that's 2 1/4 or 9/4. Okay, so that gives me our c value immediately. And the final answer, the actual answer for this initial value problem now, is this function, except with a 9/4 right here. Great, so there's a second way that we can, a second method to apply the initial condition that we can use to solve for c. And this is going to come in handy a little bit later in the course, but we'll talk about it here anyway. So this method actually happens a little bit before we find the solution. So if we go back to the step number 3, see if we can copy and paste all of this. let's go back to this step 3, just before we integrated everything. Okay, so here we were. What we're going to do now is, instead of doing an indefinite integral, we're going to integrate the entire equation between the two t values. All right, so we're going to integrate all of this dt from t equals the initial value, t equals 0, to t equals t. Now, to be more proper about this, this is sort of like not kosher, because we're differentiating with respect to t, and then we're also integrating with respect to t. So there's a little bit of confusion of what variable is being differentiated and integrated. What I should write to make it proper is either some other variable, maybe s here and s here, but I'm just going to keep it with respect to t, because we'll see what happens pretty easily. Okay, so on the left-hand side, the integral of a derivative is just a function. But since we have definite limits of integration, we plug in t everywhere we see a t. And that's sort of the confusing part. So we just leave it as the original product. Oops, sorry about that. There we go. And on the left-hand, on the bottom side, we plug in 0 everywhere we see a t over here. So this is e to the 0, y of 0. Okay. On the right-hand side, our integral from 0 to t of this is sort of where we use exactly our integration by parts. So if we go back to our integration by parts, this was the integral that we got. This was our antiderivative. Right. So let's see if we can. Doesn't seem like we might be able to copy that. Okay. So on this right-hand side, we would get our exactly 1/2 t e to the 2t minus 1/4 e to the 2t. That was our antiderivative of t e to the 2t. And we would just evaluate that from 0 to t. And again, this is, this should either be an s or this should be an s. This is, but since we know what we mean, then we won't have to be that proper. So what we get is the actual function itself minus its value at 0. So we plug in 0 there, and that goes away, minus 1/4 e to the 0. So we just get minus 1/4. And now let's see what happens. So let's solve here for e to the t times y. It equals 1/2 t e to the 2t minus 1/4 e to the 2t. And then we have plus 1/4 here, and we have this term. So plus e to the 0 we know is 1, and y of 0, this is where we now use the initial condition. Y of 0 is 2. So we go back here. This is 1 times 2. That's a 2. And you'll notice what happened here. If I divide now by e to the t, I get 2 plus 1/4 is our 2 1/4, which was our 9/4. And I divided by e to the t, so we get our e to the minus t. We end up at the same solution that we had before, except it's just a different technique. And we can compare this 9/4 e to the minus t to exactly what we got before, 9/4 e to the minus t. Okay, so this is a second method to apply the initial condition that in some cases will be more beneficial because you do the initial condition, you apply the initial condition right when you're integrating. So you sort of do two things at once. You integrate and you apply the initial condition. What we did over here was split up. So we solved the entire problem first, and then we went back and we applied the initial condition. Both methods will give you the same result, but as I said, sometimes one will be more helpful than the other. So now that we've gone through applying the initial conditions and solving non-homogeneous folds, you'll be doing a lot of that in your homework. Let's take a second now to see if we can switch gears a little bit. So these in-class exercises that are labeled these CTs are going to be exercises that I've either designed or reproduced from either your book or another book that focus on critical thinking. So this is, as I described in the syllabus, the other half of one of the focuses of this class. One half being able to do computations and solve differential equations like we did here. The other half is sort of building your understanding of higher level mathematics. So this is problem 18, which is also on your homework on page 10. And let's see what it says. So it's a very neat problem, and it's actually very instructive. So it says, show that if A and C are positive constants, and B is some real number, could be positive, could be negative, could be 0, then every solution of the equation y prime plus ay equals b e to the minus ct has the property that the solution tends to 0 as t tends to infinity. Okay, so give this a shot by yourself for a few minutes. This might take a bit longer to make some progress on because it is meant to be one of the more abstract problems. And then we'll come back and talk about the solution. Okay, so let's talk about the solution. So remember that A and C were positive constants, but B could be positive, negative, or 0. A lot of times when we're dealing with problems of this type where what to do doesn't immediately suggest itself, we try to figure out some sort of approach to the problem. So let's figure out, as a general rule, for really any problem we'll do in this class, first thing you should figure out is what you're being asked for. So what you're being asked is to show that blah blah blah, every solution has the property that this is true. So I'm just going to underline it. Show that every solution has the property that this is true. That's exactly what we're being asked. So that's the first thing we want to focus on. The second thing we want to focus on is, okay, they have to give us some information to figure out what the answer to the problem is. So these are the two bits of information. A and C are positive. Well, I guess there's 3. B is a real number. And these are solutions of this equation. Okay? So these are all things that we are given. So they're answers to the question, what are you given? Okay. Our third step in our sort of little problem solving procedure is to use what we're given to somehow get us to where we want to get. Okay. So if we're going to show that y goes to 0 as t goes to infinity, well, we really need a function y, right? We need the solution to this equation. Luckily for us, that's exactly what we just talked about. This is a first order non-homogeneous equation, and the coefficient of y prime is 1. So let's go ahead and find our integrating factor. So it's e to the integral of whatever's in front of y, which in this case is the number a. So it's e to the at. So now that we've got our integrating factor, we can multiply through by it. So once we do that, on the right-hand side, we're going to do a little bit of simplification. Remember that e to the at times e to the minus ct, same base, so we add the exponents. And I'm going to subtract the t here. Okay. All right. So the left-hand side, we're guaranteed is the derivative of the integrating factor times y. So it's looking like we're in pretty good shape. Now, this is the point where we might want to start to worry, because if we integrate both sides, on the left-hand side we have this, on the right-hand side we just have this integral. Here's where we notice that things are getting a little bit more complicated. We have to be a bit careful. We have a minus c here, and let me just make the first simplification b is a number, so I can just pull that out. And I just want to do that so that we can focus on integrating this part. we know that a and c are numbers, and we know that they're both positive. So if you think of a and c, maybe a is 1, let's say, but what if c is also 1? Then the thing we're integrating is just the integral of 1. However, if a is 1 and c is, I don't know, well, let's make a 5 and c 2, then we'd be integrating e to the 3t. So depending on what a minus c is, we get a different function. So we have to take that into account. So we're going to say that this integral is different depending on whether a equals c or a is not equal to c. So let's do the a equals c part, since that's pretty easy. If a is c, then this is e to the 0 times t. So it's just the integral of 1 dt. That's pretty easy. If a is not equal to c, well, then we have the exponential of some number times t. And that's just a little harder, but we know that that's 1 divided by that number times the exponential again, plus c. All right, so now that we've figured out what our integral is, we notice that our solution has two different cases. So our first case, when a equals c, then our left-hand side is unaffected, but our right-hand side is t plus c times the b. So bt plus some other number. If we solve for y here, we get bt plus some other number times e to the at. And we'll use that in a bit. But let's finish the second case. So if a is not equal to c, our left-hand side is still, again, the same thing. But the right-hand side is now this slightly uglier mess. Now remember, we need to multiply all of that by b. Okay, so we get b over a minus c times e to the a minus c t plus some other number, and that's b times c. So we solve there for y, and it's going to look a little strange, but here's an e to the at. It would be downstairs here, and that would cancel out with this e to the at, leaving us e to the minus ct, plus d divided by e to the at. We'll just leave that in there. Okay. So these are the two solutions that we get in the two different cases. Right. So at this point you might be saying, okay, I'm done. But unfortunately, that's not exactly what the problem asked, right? So it wanted us to show that every solution has this property. So now that we've found all the solutions, let's show that. Okay? So if you're in case 1, the solution we get, this guy up here, we want to make sure that as t goes to infinity, y goes to 0. So let's find that. That's a limit. Okay. Now, even though we get infinity over infinity, there's a few things that you could do. If you studied and learned L'Hopital's rule in your class, you could certainly do that. The derivative of the top is just b. The derivative of the bottom is going to give you another exponential. So this thing will go to 0. Or you can just realize that the exponential grows much, much faster than a linear function. So you're getting linear growth divided by exponential growth. You get a much bigger number in the denominator. So your fraction goes to 0 as t goes to infinity. Okay. We can do the same thing for same sort of analysis for case 2. We're taking limit as t goes to infinity of y of t, except now we have a different function. We have this function. Now this one is a little easier to understand. We know what e to the minus ct looks like, right? And for our example, e to the minus ct looks like that. And again, it's important in both of these, and I should have mentioned that here, that a and c are positive numbers. If a or c was a negative number, then this might come upstairs, or this might be just e to the some positive number t, and that would go off to infinity. But since c is positive, e to the minus ct, this goes down to 0. And since a is positive, this bottom function keeps growing and growing and growing. And a number divided by a very large number, we learn from calculus, gets very close to 0. So we get 0 plus 0, of course 0. Okay, so that tells us exactly what we wanted to show, that the function goes to 0 as t goes to infinity. And that's the solution to the problem. So we've now shown in both cases, the only two cases there are, that this statement is true. So that completes the solution to this problem. So you've now seen a good example of what I would call an exercise that involves critical thinking. And throughout the semester, we'll do things like this, both in class and also on your homework. And they'll show up on your exam and also maybe on your quizzes. So we want to make sure that we are studying these examples so that we can get a better grasp on not just being able to compute solutions, but understanding what these solutions mean and what these different properties of these solutions are. So there's a different way to arrive at a formula, just like we did, a procedure for solving non-homogeneous folds that is going to come in handy in chapter 2, actually. So let's see what this is to end today's lesson. So this approach is called variation of parameters. And things in math are usually named pretty appropriately. So if you think back, every single solution we've gotten for a first-order equation involves a parameter. That's what the plus c is. And variation of parameters means we're somehow going to let those parameters vary. And as we'll see, that's going to give us an alternative but equivalent way of solving our non-homogeneous equation. All right. So we know that from everything you did yesterday, the homogeneous solution is given by this. That was sort of our formula for the homogeneous solution. And here's our parameter c. So what we're going to do now is we're going to make the constant c into a function. We're literally going to let it vary. Make it a function of t. So that y of t now becomes c of t times our exponential. Okay? And here is my question to you. Let's see if you can find the new differential equation. It's going to be, again, a first order that c of t satisfies. Okay, so again, this is another one of these critical thinking exercises because I'm not asking you to compute a particular function. I'm asking you sort of a higher level question. See if you can derive the equation that c of t satisfies, knowing that y of t is related to c of t in this way, and that y of t satisfies this differential equation. All right, so give that a shot for a few minutes, and we'll come back and talk about it. So let's see how we can relate this equation and our new variation of parameters equation together. So we know that this is the same y that solves this equation. So we can just try to come up here from 1 and try to find the derivative of both sides. So on the right-hand side, we have a product of functions. Here's one function, here's another function. So we'll do the product rule. The derivative of the first times the second. Let me minimize this. Plus the first times the derivative of the second. I'm going to write this out here just because we want to be a bit careful in taking this derivative. Okay. So let's do that here sort of as a side computation. So I know that if I differentiate any exponential, I will always get back the exponential. But then I also have to multiply by the chain rule by the derivative of whatever the exponent is. So the derivative of the integral of a of t is just a of t. All right. So we can figure out that the derivative of this particular exponential is minus a of t times that same exponential. Okay, so that's our side calculation. So we're going to go back up here and use that. So our y prime is the derivative of c times this exponential minus the function a of t times that same exponential. And I'm going to want to simplify this a bit just because there are some things that factor here. So c prime minus a, that factors, times this exponential. Whenever possible, you should simplify things. It usually makes the math easier. So we have our y prime here. What we're going to do with this is plug it into this equation and see if we can get any simplifications. And we're also going to plug in our original y since it's right there. Okay. All right, so y prime plus ay equals b. This yields our term right here. Plus a times y, and y was exactly our c e to the minus this. All of that equals b of t. Okay. All right, so at this time, we want to see if we can make any simplifications. And let's go back here and notice that I did forget one small correction here. Once we calculate our derivative, we should have had it multiplied by c. Right? So here is an a, so there should be a c in front of that. One of the downsides of recording these videos is, of course, I don't have all of you to help me in case I forget something. So I have to catch it later on. So that c belongs there, and it also belongs over here. So let me just put that in. The reason why we needed that is because you'll notice now that here's a minus ac exponential plus ac exponential. So these terms cancel. So this tells us that c prime times the exponential equals b. So I can solve for c prime pretty easily. I can say it's b divided by this. Now if I have b divided by e to the negative something, doesn't matter how complicated that negative something is, it's the same thing as e to that something. Okay, so that's one of our properties of exponentials. So this is the differential equation that c satisfies. And it's such a simple differential equation that we can solve it really easily. C of t is literally just the integral of this. So the integral of b of t, e to the integral. And here I'll be proper, and I will change these limits because I want to make sure I integrate at the end with respect to t. Okay. So this is what c of t satisfies. And you might be wondering why we did all this work. Well, if we take c of t, and now we go back here to our original solution was c of t times that to the homogeneous problem. We are now claiming that this y of t, c of t e to the negative integral of a of t dt, the claim is that this solves y prime, in other words, the non-homogeneous problem. It shouldn't be a surprising claim because that's exactly what we just did. We plugged this into here, which is already the non-homogeneous part, and we derived our C of t formula. Okay? So it shouldn't be that surprising. But let's use the C of t formula in here and see if we can make a bit more sense of what's going on. So our C of t formula is this. Okay? One thing that we'll do explicitly here is we can just take C of t. We know we're going to integrate here, so we're going to end up with an integration constant out here somewhere. So let's go ahead and just add that in, since we know that's where we're going to get. Let's go ahead and use D instead of C, so we don't have too many C's. All right. So this is what we get. This is our e to the minus a of t dt. That's still there. And our c of t, we've now plugged in this entire expression over here. Okay. The reason why this expression is important is because if you were to have done this problem in a very general setting, then this is exactly the formula we would have gotten for our solution y of t to our non-homogeneous problem. Okay? And it may look a little strange, but notice that this is 1 over mu. Right? This is exactly 1 divided by the integrating factor. The integrating factor is e to the integral of a of t. E to the minus that is dividing it. Right? This is an arbitrary constant plus b of t, and this is also the integrating factor. And now I can go ahead and make this a t dt. Okay. So this formula is exactly what we would have gotten had we solved this problem in its most general form. This is why I left this toward the end. I didn't want to flash this up in the beginning. But in case you're interested more in formulas, which I highly discourage you to memorize formulas, but in case you're interested in a sort of one-shot formula to solve for y of t, this is exactly what we've just arrived at. And you can see page 7, equation 12 is what we've just arrived in your book. So that completes our lesson for today. Your homework is going to be more of solving these problems using these integrating factors. And it's also going to include a few of these sort of theoretical problems. We didn't come back to our coffee problem, so we didn't come back to solving this equation, and that's because it's part of your homework. So for homework, I actually want you to solve this equation and see if you can come up with the temperature for coffee. And if you're interested at some point, then maybe you can model this temperature for your particular coffee problem and see if it agrees with the actual coffee temperature that profile that you would get if you left coffee out to cool. All right, so I will see you all on Friday. So remember to come to class normally.